Assalamualaikum warahmatullahi wabarakatuh and very good morning. Uh, so today actually we learn about a new topic. We call it as non-metric multi-dimensional scaling, or short term we call it NMDS. So previous class you already learned about a few topic about PCA, CA and DCA. Is it right?
Yes.
Yeah. Okay. Can you explain a little bit, Wani? What is PCA?
PCA is a multivariate technique that can reduce the data dimension while accounting the original variation in a new set of variables.
Okay. Nini, DCA?
DCA is a classification to describe the differential features of object from several populations.
Okay. Actually, PCA, CA, DCA for NMDS or non-metric multi-dimensional scaling is fundamentally different all of that method. Okay, it's about for this method we use the ordination based on ranks, as is determined by rearranging points in an iterative way to find the best order solution. So for the major advantage of data can be non-normal or arbitrary, discontinuous or questionable scales. Okay, to avoid assumption of linear relationship among variables. This is the major advantage of NMDS. Okay, the basic idea. Kak Ayu, I think I already given you a task about this. Can you explain a little bit about this basic idea?
So we find the dimension of two dimensions by compress the point into a space so that we can find the distance between the point.
Okay, thank you, Kak Ayu. Okay, this one is the point, the plotting of the variable by the dimension. Next step, we will see what is the method that we can find using this idea. Okay, one of the idea is to do the by projection. So the another method is to compress point to a surface. As the objective of this method is to see whether the point is close point is will stay close and far point will stay far. Okay, some approach of NMDS non-multidimensional use a pre-specified number that's small of axis or dimension, usually less than equal 3. Data is converted to a dissimilarity matrix among all pair of sample. Point in additional ordinations are rearranged in iterative fashion to find the lowest dimension solution. And last one, a solution is found such that the rank order of distance between points in the ordination match the order of dissimilarity between the point.
Is it this method we have to rearrange the order of distance between points?
Yes, Kayu, we have to rearrange from the small to the big. Okay, after we rearrange the value, then we can plotting it by a Shapiro. Let's see from here a Shapiro diagram. So the relationship between dissimilarity and distance. So for distance, we can use the method of Euclidean, and dissimilarity we can use the Sorensen. Okay, for the finding the best rank order solution, so rank order agreement of distance and dissimilarities is achieved by fitting a monotonic regression. What is monotonic regression, Nini? You know? You know?
I don't know.
Okay, of the ordination is onto the dissimilarity. Okay, what is monotonic regression? Regression is a non-parametric method of finding a least square fit based on rank of the dissimilarities. Okay?
Is it similar to the fitted value?
Yes, Kayu. Okay, this is a diagram with monotonic regression. So, all of you, what you can explain a little bit about this diagram? Give some idea.
I think you have an idea.
What's Kayu?
The red line. Maybe the red line is the fitted value for the distance, which is we call it monotonic regression, and then the point is the point between distance versus dissimilarity. Is it?
Okay, thank you, Kayu, for some explanation. Let's see next slide. Okay, the basic idea for the monotonic regression, as you can see the red line, this is the monotonic regression. So we will find the stress between the point this one until the point of this monotonic regression. And then this will repeated many times until then we get the smallest stress. Okay.
Okay.
So we can see. Okay, we can see here. Reducing stress in the solution. Stress decreases as the rank order agreement between distant and similarities improve. Thus, the aim is to find the solution with the lowest possible stress. Okay, we want to find the lowest. Okay, there is no algebraic method of finding the best solution. It must be found by an iterative search or trial and error optimization process. Means we will repeat it until we get the lowest possible stress.
Then we repeat the regression line, monotonic regression line.
Yeah. Okay, good. Okay, we can see here from the example of an MDS. I think it's more easiest way lah. You can understand. So here you can see here densities per square kf of 7 large mammal species in 9 areas of Rwenzori National Park, Uganda. So how much the variable here?
7.
7. Elephant, warthog, hippo, waterbuck, cock, topi, and buffalo. Okay, first step, create a dissimilarity matrix among the 9 areas. So as I said before, that we use Sorensen's measure only in upper triangle without the zero diagonal. As you can see here, area 1 and area 2, you get the dissimilarity 0.3626. Area 9 with area 8, what is it? 0.2254. Okay, and then we plot ordination generated. We plot it randomly. Okay, so far I learned about the theory, so I think you have some idea what is the idea about NMS, NMDS. Okay, so all of you, let's discuss together. I think we can put some discussion here. From this, okay, we start with the diagram first. This diagram. Okay.
Okay, for this example, we plot the distance versus dissimilarity. And then after that, we get the monotonic regression line. And then from this monotonic regression line, we find the stress, based on this monotonic regression line.
Okay, next is we recalculate and the process iterated until the maximum achievement. Means that we repeat the process until we get the minimum stress, which is in the iteration 30. Okay, now we want to look how much the stress change. So to look how much the stress change, we plot stress versus the iteration number. Once the stress start to level out, so the stress level out, which means the stress will give the lowest values and the iteration will be the lowest too. And then we plot until that we can see the final. Okay, from this plot, the above plot, we can get or we can see the lowest value of stress is 1.36. So if we are using this 1.36, we can get or we can observe that there exists 2 dimensions, which this will be the first dimensions and this will be the second dimension. Previously, we can see that there exists 2 dimensions. So if you want to do a confirmation or the validation on how much the number of the dimensions should be, so we can use a script plot that can guide a determination of the number of dimensions. So based on this script plot, we plot with stress versus the number of dimensions. A break in the slot beyond which further reduction in the stress are the smallest and suggest dimension. So we look into the elbow point of the script plot, so that should be the number of the dimension. So based on this script plot, we can see that 2 should be is the good or the best number of dimension. Lastly, there will be a stress guideline for NBS interpretability. Okay, the stress will be can be divided into 4 categories, which if the value of stress lower than 5, it will be the excellence. So no prospect of misinterpretation. And if the value of stress between 5 and 10. So it will be good with a little danger of throwing false interference. 10 until 20 will be a fair, usable, but some distance will be misleading. And if the value of stress will be greater than 20, it's very poor, which the ordination may be dangerous to interpret.
The conclusion is why we use the smallest value of stress is we want give the misinterpretation of non-classical MDS.
Okay. You understand?
Okay.
Alright.
Okay. So that's all for today, and thank you.
Okay, thank you.
Bye.
Bye, doctor.